Thank you, James. Hello, everyone, and welcome to this year's SPDK PMDK Intel Performance Analyzers Virtual Forum. My name is Olasoji Denloye. I'm a software engineer at Intel, and today I'm going to talk to you about building Java solutions with persistent memory. In this presentation, I'll start with the motivation for why to build Java solutions with persistent memory, and then I will talk about a specific library which we developed called the Low-Level Persistence Library, or LLPL. I'll give a little bit of an overview into what the library is and how to use it. And I'll illustrate this with some sample code, which will be a simple array. And then I'll end with some additional features, some new features coming to the library that will give us more flexibility and performance. And after that, I'll take your questions. So first off, why Java? Java continues to be a popular language for building data center applications, such as databases. These big data frameworks that you can see the logos for are only examples of Java applications in the big data space. Now, why persistent memory? Persistent memory boasts that it offers new ways to program with long-lived data and that it would optimize the data center. Well, persistent memory is fast like DRAM, and it's persistent like storage. And so some of these Java frameworks are using persistent memory to build things like persistent caches and persistent storage, mostly all for the performance benefits. So why LLPL? Why create a Java library to enable persistent memory programming? On the list on the right, we can see that from Java 11, there is the option to allocate all of your Java heap on persistent memory, but that's a volatile application. That means that once the JVM exits, all of your data is lost. And so that provides some limitations as to the kinds of applications that you can build with that. The next is persistent map byte buffers from JDK 14. This is an optimized way to use map byte buffers that are backed with persistent memory. The drawback here is that you're limited to the byte buffer API. We also have Java bindings for PMDK. Now, PMDK is part of the persistent memory development kit. It's available from JDK 8, the Java bindings. And PMDK is a key value store that is optimized for persistent memory. But that's what it is. It's a key value store. So what low-level persistence library does is that it gives you the greatest flexibility. You can build a key value store or an array or something much simpler. So it gives you the greatest flexibility for enabling persistent memory programming in Java. Now I will talk a little bit about the said low-level persistence library. It was developed by Intel. It's an open source Java library for persistent memory programming. It's a component of the persistent memory development kit PMDK. It is also compatible with JDKs 8 and newer. It is production quality and it's available on GitHub and Maven Central. As a library, these are the heap, memory block, and transaction. These are the three main classes that make up the backbone of this library. A heap is simply a pool of persistent memory with an allocator. You can create a heap, open a heap, and allocate persistent memory. A memory block is a Java wrapper around allocated persistent memory, and it offers APIs to read and write to persistent memory. A transaction is a mechanism for grouping transactional allocations, deallocations, and writes into one single transactional operation. Now, there are three kinds of writes that are possible with persistent memory from a data consistency point of view. The first is volatile. Okay, so we know that persistent memory is cache coherent, which means that loads and stores to persistent memory go through the cache hierarchy. And so a volatile write is simply a write that goes to the cache and will eventually be flushed to memory or main memory or persistent memory. Now, because most CPU caches are typically not durable, when there's a power loss, all of that data is gone. So that's the first write, a volatile write. Now, persistent memory is also durable, which means that in the case of a power loss, the data on it is still accessible. And so you can imagine certain applications like restartable caches could use depend on that property of persistent memory. So now, if you want to make sure that your data is accessible and consistent after a restart, simply writing to the cache is not sufficient because your cache is not durable. So what you need to do there is write to the cache and flush the write from the cache. So that's the second kind of write, a durable write, which is a write and a flush. Similarly, a flush can be interrupted in the case of an unexpected power failure or crash, right? So in the third type of write is a transactional write. And this guarantees that data is accessible and consistent after a power failure or crash. And how this is done mechanically is it's a backup, a write, and then a flush. So these three kinds of writes are all supported in LLPL. This table here shows the three kinds of heaps and the three kinds of heaps and memory blocks and the corresponding writes that they support. So here we can see there's a transactional heap and transactional memory block, persistent heap and persistent memory block, and a heap and a memory block. We sometimes refer to the heap as just a general heap. So with the general heap and an allocated memory block from there, all kinds of writes are possible. But by default, the writes are volatile, which means they just go to the cache. Now, on a general heap, you also have the option to do a manual durable write, which is a write and a flush, remember? And on optional transactional writes, which is a backup, a write, and a flush. So because these operations are optional and manual, it's possible to forget to either do a flush or perform a backup. And so a general memory block does not offer any kind of guarantees as far as data consistency after a restart or a crash. A persistent heap and a persistent memory block, on the other hand, the default kind of write is a durable write, which means all writes are flushed automatically for you, so you cannot forget to flush. So therefore, a persistent heap is useful. A persistent heap and persistent memory block, you can use that in applications that that guarantee data consistency in the face of a controlled shutdown, like a restart. Transactional writes are also optional and manual on a persistent heap and persistent memory block. Now, finally, a transactional heap. Volatile writes are not possible, durable writes are not possible. The default kind of writes are, like you guessed, transactional writes, where the writes are backed up and written and then flushed. And so using a transactional heap, even if your application crashes, you have guaranteed data consistency there. You cannot forget to flush or forget to back up your data. And again, all of these three heaps and memory blocks are available in LLPL. This slide shows the access methods, the read and write methods that are available on memory blocks. I know I talked a lot about the writes. So a typical write would be a set byte short int or long, and a get byte short int or long. We also have copy methods that copy memory from a byte array to a memory block, or from a memory block to a byte array. You can also copy memory between memory blocks. Other methods include a free method, handle, and an is valid. Now, free, I should remind you that our heaps in LLPL is not the same as the Java heap. And so there's no garbage collector. And so allocations have to be manually freed. And so that's why a free method exists. This is new for Java programmers because you're probably used to the GC taking care of this for you. In addition, we have a handle method on a memory block. What is that? A handle returns a long value, which is a stable value that is used to identify that memory allocation. And that long value can be used later on to reaccess this memory block. We'll see more of this usage when we're going through the sample code. And is valid on a memory block. That just helps you, as the name suggests, it tells you whether this memory block has been freed or not, if it's valid for use. And now we'll go into the sample code, which is a simple array. It's a long array. I'm going to go through two Java classes, a long array.java, a long array example.java. And I will, as I'm going through this, I will explain some basic concepts in persistent memory programming with Java. So conceptually, our long array is going to consist of just one memory block, and we're going to store all the long values inside of that memory block at different offsets, right? So the first thing that we have here, lines 1 and 2, clearly we've seen that we have chosen to use a transactional memory block and a transactional heap. What this means that every write to this memory block, every write to this array will be transactional in nature. And so even if there's a crash, all of the data in this array will still remain consistent. So line 7 represents the array block that holds all of the data for our long array. Lines 5 and 6 are fields, are convenience fields that we use that will help us later on to navigate through the offsets in this memory block. It's not necessary, but it's very useful and for code clarity. So let's start off with line 9, which is a constructor. So given a transactional heap and a size, we're going to construct this long array. And on line 10, we call allocate memory block, which is a method on the heap, given the size, given the number of elements long elements that we are going to store in this array. So allocate memory block returns, as you might imagine, a memory block. And what we're doing here is the size, we're going to make sure it's large enough to fit all of the elements in the array plus our header. Now our header is about 8 bytes, and we're going to write the size of this array into the 0th offset of the memory block, which we see on line 11. So just to let you know, in case it's not apparent to you, on line 10, we actually allocate persistent memory, and on line 11, we actually write to persistent memory in a transactional way. On line 14, this is a factory method from handle, which we use to reaccess a previously constructed long array. So given a heap and a handle. I talked about a handle earlier, and this is useful in order to reconstruct a memory block or reaccess, in this case, our long array. So on line 15, using the memory block from handle method on the heap, given a handle, it returns a memory block that is associated with the previously allocated memory block associated with that handle. And so line 16 just calls our private constructor, and it stores this reaccess memory block into our long array. The code is too long, so it's compressed a little bit. So the remainder of the code is on the next few slides. So on line 23, these are the, starting from line 23, these are the main methods in the array, if you will, the set and the get. So on line 23, that's a set add index. So you set the given value at a given index in the array. And now we also call set long on the array block, which is the write to persistent memory. And the first argument is a long, which is the header size plus long.bytes times the index. That helps us figure out the offsets within that array block to store the given value. Similarly, on line 27, we have a get, which given an index, it retrieves the value, the long value stored at that index in the array. So what we do internally, we just read from the memory block. And again, header size plus long.bytes times index helps us figure out the offsets within the array block to get the given, to get the value. These next three methods are very useful, and they're like convenience methods for the long array. As you can imagine, size returns the size of the array. And remember, we wrote that at the 0th offset in the memory block. Again, size offset comes in useful. Having these constants comes in useful here. The handle method on line 35 is very important. And we saw that earlier because it allows you to access the stable long value that we're going to use later on to reaccess this long array. Maybe when we reopen the heap or sometime after in a subsequent access. And again, the free method on line 39, as the name suggests, it frees the array, the corresponding array block for this long array. So that's a simple long array, and that's really all you need in order to implement the basic array in LLPL. So this next Java class is called long array example, and what it does is it just creates the array, and puts some values inside and reads it back out. So in the first few lines, helps us create the heap if the heap does not already exist, or open the heap if it already does exist. And these are methods on heap. So heap.exists, create heap, and open heap. So since this is our first time around, the heap does not exist. So what we'll do is we'll create the heap on line 11. And create heap takes a heap name and a heap size. In this case, our heap name is mount mem long array. And what this means is that on my system, mount mem is the location of my persistent memory namespace. A long array just represents the file. And line 8, the heap size is going to be about 20 megabytes. So it's a small heap. Now, if this is our first run, we're looking at line 13. What we're going to do is, again, what we plan to do is create the array and set some values in there. So on line 17 is where we create the array. But on line 16, we see a transaction dot create. Now, remember I said a transaction is a mechanism for grouping transactional allocations, deallocations, and writes. So what we want to do here is we want to make sure that that the creation of the long array and the setting of those values at indexes 5 and 7 all happen together. And if an exception happens or there's a crash or whatever, we want to make sure that all of that memory gets rolled back. So that's what the transaction helps us do. So in order to create a transaction, we call create on the transaction, and given a heap and a lambda body. So the lambda body is what contains the transactional writes or allocations or deallocations. Okay, so on line 17, we create a long array of size 10. 18 and 19, we insert values into the array at indexes 5 and 7. And by line 21, this transaction has committed. It means it was successful. It means the array has been created and initialized. Now, line 20 introduces a new concept, which is called the root. Now, a root is a fixed location in the heap where you can store any long value. Typically, you would store the handle of a memory block so that you can re-access it later on. The reason for the root is for bootstrapping your application. So in this case, our array, we're going to store the handle of our array in the root location so that in a subsequent run, we'll be able to re-access that array. And we'll see that from line 23. Okay, so now lines 23 and 24 and so on. This is where we re-access our long array. Again, we remember the factory method from handle on the long array, and we supply a heap and a handle. The handle is what we stored in the root using the heap.setRoot, if you remember. And so we just do a call heap.getRoot method to get the handle of the long array that we just created. Lines 26 onward iterates through all the elements of the array and gets the value, retrieves the value. So 27 is the array.get, get at index. And hopefully, when you run this, actually, you will see at indexes 5 and 7, you'll see the values 10 and 20 respectively. So this is how you would create a long array and create a heap or open a heap and store your data structures into the heap and store values into the long array and retrieve the values. This is a very simple example, and it illustrates just how simple it is to use LLPL to start creating whatever Java application for persistent memory that you need. So just quickly, we went through a lot of APIs and methods, and just as a summary, I wanted to go over them really quickly. So on the heap, we saw the exists call. We had this idiom where, if the heap exists, then we'll open the heap. If not, we'll create the heap. That's a very useful idiom to use. We also saw the setRoot and getRoot methods. This helps with bootstrapping your application. You can put the handle of a data structure or handle of a memory block at the root. And when you re-access the heap in a subsequent run, you can call the getRoot method and get that handle and reconstruct your memory block or or data structure and carry on with your application. Also, allocate memory block. It's given you give it a size and it returns to you a memory block object. Similar, and it actually allocates persistent memory. Memory block from handle is a way to reaccess a previously allocated memory block. It does not allocate any new persistent memory. The APIs that we saw on the memory block include set long, get long. Remember, there's also set byte, set short, set int, and the copy methods, but we didn't see them in this example. We also looked at the handle and free methods. Again, the handle method returns a stable long value, which we can use which is associated with that memory allocation. And you can use that handle to reaccess that memory allocation, whether it be a memory block. Also free is new for Java programmers because, as I said again, this persistent heap is not garbage collected. So you have to free your allocations manually. We also saw a use of a transaction, and you call the create static method on the transaction, given a heap and a Lambda body with the transactional operations that you want to group together and have execute atomically. Okay, so now we've already seen some of the functional features of LLPL and the API. And now I want to talk a little bit about performance. So the baseline performance that you get from using LLPL or even persistent memory is that the first one is obviously GC pressure. So because we're not using the Java heap, we're not using the Java garbage collector, and so the usual problems that we see with garbage collection, whether it's uneven pause times or whatever the case may be, we don't have those problems here because it's manual object deallocation, because we use manual object deallocation. Also, another baseline performance advantage that we get using persistent data structures is that you tend to have a simpler architecture and less code. So we've seen in in some big data application, the use of log structured merge trees. Some of them have like multi-levels where they store data in memory and on disk. And so let's say on writes are buffered in memory, and once it reaches a certain capacity, it gets flushed to disk. And once it gets to disk, it now becomes immutable. And then on reads, because the disk is slow, in order to optimize the speed of the reads, there are a whole bunch of data structures like Bloom filters and indexes that help you minimize seeks. So makes a complex architecture. Whereas with a persistent data structure, you can simply, persistent memory acts like memory and storage. So you can simply write persistent objects in memory. And so you don't need to serialize or deserialize objects as you go back and forth. And you can also update in place. So these are some of the baseline performance advantages that you get with using persistent memory and LLPL. And so now I'll talk about some of the performance features that we've put into LLPL. So the first one is compact allocation. So a regular memory block, like we've seen in the example, it uses the first 8 bytes of the allocated memory to store its size. So that means that every time you allocate memory, we're actually adding about 8 bytes. Well, we're adding 8 bytes to the size of that allocation. So in contrast, a compact memory block does not store its own size. Now, this is useful if the size of the memory block is known statically in the code, and you don't want to spend that 8 bytes of persistent memory. You don't want to waste that 8 bytes because you already know the size. And so because of that, there's the size method on compact memory block goes on a supported operation exception. By the way, a compact memory block is the same as a memory block except for this size method, and by the fact that it doesn't store the size. And so in order to create a compact memory block, it's the same way, it's a similar way to the regular memory block. It's just that we call allocate compact memory block and compact memory block from handle. And also we have persistent and transactional flavors of compact memory blocks. So in this long array example, I've just replaced transactional memory block with transactional compact memory block. And on line 10, where we actually do the allocation, the memory block will be 8 bytes smaller. Now, this does not seem like a huge savings, but imagine once you start having millions or billions of allocations, this size overhead can really add up, and especially if you don't need it. Another optimization is what we call range operations. Now, range operations, they're an efficient way to write within a contiguous range of bytes within a single memory block. So going back to our array example, imagine if we needed to write a fill method, which what it does is it takes a value and writes that value to all of the entries within that, all of the indexes within that array. This is lines 1 to 7 show how we might write such a fill function. So on line 2, you can see we have a transaction. It makes sense to use a transaction because you don't, if an error occurs or there's a crash, you don't want the array to be partially filled. So we have a transaction there. And then what we do, as you can imagine, we iterate through the array, and for each value, for each index, we write the given value. Makes sense, right? But what this means is, again, because for example, in this example, because in the transactional memory block, remember we back up, we write, and we flush. And all of those operations are done automatically for us. So in the first part, on line 4, for every element in the array, we're actually doing a backup. So what these range operations help us with, so now we're looking at line 8. It's the same thing, but written with using ranges, and I just called it fill with range. So array block with range, what it does is it will do just a single backup of the entire range of bytes that we're trying to write to. So the first argument is the range of bytes that we're going to be modifying, and then we have a consumer of a range where we then write like normal. So lines 11 just does a regular set long. It essentially does the exact same thing as the fill example, the example on line 1, but instead it's just a single backup. And this can have some significant performance advantages. Range operations, they also exist with memory block creation. And you can use them to allocate and initialize in a single operation. So again, going back to our long array example, on line 1, this was our constructor. This is what it looked like. On line 2, we allocated memory for this memory block. And on line 3, in a separate operation, we initialized the size field, if you will. This is where we would the size of the array into the 0th offset of the array. So what ranges help us do here is you can sort of combine those two operations into one transactional operation. And again, just with a single backup. The next optimization is the use of accessors and object-free allocation. Now, an accessor has a similar API to memory block as well, but the only difference is that it is repositionable. So you can use an accessor to iterate through multiple allocations without creating too many Java objects. So you create an accessor by calling heap.create accessor, and you can reposition said accessor using a handle method. Now, this handle method takes a handle and it will reposition that accessor to the given memory allocation associated with the given handle. So now another optimization that goes hand in hand with the accessor to handle is the object-free allocation. And we do that using heap.allocate memory. So this table at the bottom just shows the two methods, the contrasting method. So in an object-free case, we would call allocate memory as opposed to allocate memory block. So allocate memory block returns a memory block, and allocate memory just returns the handle, which is so long. It returns the handle of the allocated memory. so it doesn't create any Java object around it. Similarly, the handle call will reposition the given accessor to the handle specified, the handle that was passed in, as opposed to memory block from handle, which will return a memory block that is associated with the given handle as well. So in one case, we get on the left, the methods on the left return object, the methods on the right don't return object. And this can be useful for, again, GC pressure, and it also helps with performance. So this is an example using an illustration of an accessor. So now we're back in the long array example, and we're going to use a transactional accessor as we see on line 13. Now what we want to do is we want to create an array. And in this array, we want to store the handles of memory blocks, or we want to allocate memory and store those handles into the long array. And then we also want to initialize those memory allocations with some value. Okay, so we start the transaction as we did on line 16. We create the long array like normal on line 17. We store the root. We set the root, the handle of the array to the root like we did before. And so here's the crux of this demonstration. So what we're doing here is we're iterating through all of the elements in the array. And on line 20, we allocate memory, 128 bytes. And what we return a handle. Again, we could have allocated a memory block and we would have gotten a memory block object back. But line 20 does not return an object. So now, so now what we do on line 21 is we take our accessor and slide it, if you will, to where to this allocation that we have just created. And on line 22, what we do is we set at the zeroth offset the current I count, and then we store the handle into our long array. So again, other than the long array, there are no objects created. And in this case, we're creating an array of size 1,000. So we're going through all of these elements, and I think the only extra object here is the accessor. We don't create any objects when we allocate any memory blocks when we allocate the memory. Similarly, on reaccess of this long array, like we saw before on line 27, we reaccess the long array from handle because we stored the handle in the root. And now we iterate through all of the elements in the array. And on line 29, we position our accessor at the allocation that we stored at that index, at index I. So we just do a get, and we position our accessor there, and we also then do a get long on the accessor. Remember, the accessor has pretty much the same API as memory blocks. It's just that they're repositionable. And so on line 30, we do a get long on the accessor at the zeroth offset to make sure that it's the same value that we wrote. On line 31, we can also free the memory using an accessor. Again, no objects were created here except for the accessor object. So we went through 1,000 elements in the array and only one object was created as opposed to, I guess, 1,000. So that's an illustration of how the accessor works. And in addition, we have different flavors of the accessor, which is the persistent and transactional accessors. We also have compact accessors as well. So now I'm going to talk about some of the new features that are coming to LLPL. The first is production quality pre-built data structures. As you can see from the list, we have a concurrent adaptive radix tree and adaptive radix tree arrays and lists. So the idea here is that all of these data structures have been performance tested and they're optimized for persistent memory. And all of the tips and tricks that I was just talking about, they're all in there to make sure that they're as performant as possible and they're useful for production quality applications. And so it's nice because they're just ready to go. The next feature is memory pools. Now, a memory pool is kind of like a heap, but there's no transaction support and there's no allocator. And the Access APIs are built into the memory pool, and it's very similar to the memory block. So set long, get long, short, int, bytes. You can also copy from the memory pool to arrays, and copy from memory pool to memory pool. Another big feature of the memory pool is that it is process shareable. So these can be used for all kinds of applications. The first thing that comes to my mind is like some kind of a message passing framework that uses persistent memory. So these are the two main features that are coming with our LLPL 1.2 release. This is going to be happening very soon, actually, at the end of June. So now I will take your question. Thank you.